Yeah, I'm sorry about that.
I have to click OK. Mhm. And maybe I also record.
Yeah, try it. Approve. It's so weird. I
Did
think,
you approve it?
yeah, I think it's, yeah, now I think it's working. Let's see.
Okay.
Um, yeah, sorry about that. Maybe next time when we speak more, maybe we can find another platform that is easy. I don't know. Um,
Well,
we,
let's see if it works this time,
yeah.
the recording.
Okay, where we? Okay, yes. You were talking about your the way you calculate these forces, and I think I got the idea. Um,
Mm.
of course, I will have to look into your book and the details. So, but why the geometric mean for the G's here?
Well, initially I was only accounting for the composition of the source mass, and that was a misunderstanding of mine because I had not fully understood how the theory is supposed to work. But it should depend on the chemical composition of both the source and the test mass.
Okay.
In the Cavendish experiment, you have the two big source masses and you have the test masses. And of course, like when you look at the sun and the moon, the Earth and the moon, they're supposed to be equal, right? Nobody is the boss there. They're multiplied, and when you multiply two masses, then the G value should also be the geometric mean because it's not like an addition. So you're multiplying the masses, so that's why you shouldn't use the average, but the geometric mean where you also multiply things.
Right, right. I see. Okay, okay. I get it.
And
Uh,
that's something that also um, Italian physicists pointed out. Um, what's his name again? Uh, De Toma, something. Yeah, so some physicists from Italy pointed that out that it should be the geometric mean before I was using the geometric mean. And he also inspired me to uh, for my approach of how to deal with um, things that are not made of quarks, like photons. They also react to gravity.
yeah.
And one can do that by looking at higher order Feynman diagrams, which include quarks. So, so that way, particles that don't have quarks can still react passively to gravity without exerting it themselves.
hmm hmm And that is explained again in your book, these
Yeah,
details.
yeah, of course, everything is explained in
That-
my book. Yeah.
That's interesting. Okay, I see. Uh-huh. That's very interesting. Just thinking about it.
Mm.
Mm, okay. Um,
Yeah, Giacomo de Toma is his name.
sorry.
Giacomo de Toma is the name of that Italian physicist.
How do you write it down? Sorry, can you write it on the chat box just that I?
Yeah, sure. He has a theory where I call it charge asymmetry theory, and basically it's a part of that. He's part of that electronic universe crowd, but not really part of a crowd. He's just working himself. But his theory is basically such a theory. And of course, I don't endorse it, but he had two good ideas that contributed to my theory.
Right, right. Can you write it on the
Um,
chat box? Ah, there you go.
yeah, sure. Mm.
Uh, I'll write it down just to see your rationale to all this. The Toma. I see. Okay, so then going back to this G, so your G is not universal as in other theories. It's really dependent on the material at hand.
Yeah, but there's still an universal G that's the G that I mentioned before in the chat that was unfortunately not saved. The chromogravity constant, which is the gravity per baryon or the gravity per quark is still constant. The only thing that is not constant is the gravity per kilogram. And so many would say, okay, why do I even need to know the gravity per kilogram if that's not fundamental, if the real fundamental thing is the gravity per quark? Well, you need to know that because when you're dealing with gravity, you're always dealing with balances between gravitational force and kinetic energy. Mass is always involved somehow. When you calculate escape velocity and free fall acceleration, you always need to deal with mass as well.
Right,
Even if mass is not what's causing gravity, you still need to deal with it.
right. So for you, just to be clear, I just want to really be clear. For you, gravity is being caused by these fundamental forces somehow, right? So
Yeah, it's depends on the density of virtual particles. So you already have all the virtual particles in the quantum vacuum, and the density of that is very high, and that's why gravity is so weak. Because if you add a few more by having these virtual particles that are coming out of the charges and hypercharges, that's like a drop in the ocean. It's very small, and that's why the gravity of ordinary objects, everyday life objects, is very small and hard to measure. You can only measure it with the Cavendish experiment, which is quite hard to do. I did it, but
yeah,
all the people who tried to do it on YouTube, they all failed. There was even a physics teacher who was trying to do that for several years, and he was always failing. Um, I guess he should have put in a little bit more effort. I had a big container and I put everything in a container and a glass ceiling over it. It was very important to seal it off perfectly so that no air comes in. You don't really need a vacuum, but it should be full. It's not a free fall experiment. Um, so you should fold it over so that the air is really sealed off.
right. But then where do you get this, given that you're saying that this density of virtual particles is very small, so but where do we get the bulk of it, the mass that we actually measure in your experiments?
The gravity, not the mass.
Yeah, right.
Yeah. Well, you don't really need to to really derive the strength of gravity from that. Although I did that in 2018, surprisingly, before I even really developed all the math for calculating the gravity of specific elements, I already derived the strength of gravity from how much virtual particles there are already in the quantum vacuum. Um, yeah, so you only need to realize that the density of those virtual particles really only depends on the number of charges. There won't be coming out any more virtual particles out of a charge just because you are accelerating it. Accelerating will inflate your mass, but it will not change the charge and therefore also not change the what is transmitting the charge, which is those virtual particles, gauge bosons.
Right.
So that's why it only depends on the number of charges
I see.
or hypercharges.
And so again, because your viewpoint is completely radical and different, where does the mass come from? Just out of curiosity, in standard theory, it comes from the Higgs particle, but in your case,
Yeah, yeah. As we discussed in the not recorded interview, um, it's explained by a part of my theory that's called charge mass dualism, and that's an extension of the classical electromagnetic mass theory, which started already before quantum mechanics and was very popular. And actually, that's where the first version of E equals mc squared comes from. It's it was developed by other people, and
mhm,
they had the wrong form factor, but and their motivation was different than the motivation of Einstein. They were basically saying that the energy that is in the force field of the electron, in the electric field of the electron, must have a mass equivalence, and it must be what's causing inertia. And using that approach, you get the result that half of the mass of the electron must be from its charge. And then when somebody else found quite a few decades later that if you account for the movement of the electron, then you find that the whole mass of the electron can basically be explained in that way. And my charge mass dualism is basically just extending that to other forces. So in 2017, I noticed that the neutrino has a very small mass, and at the same time, it's associated with a weak force, which is extremely weak. And so I had the idea that there's a correlation between the coupling constants and the masses of particles. And when you try that naively, using just some standard coupling constants, you don't get the masses quite right. You have to account for the running of coupling in a meaningful way. You have to, when you look at the proton, you have to actually use the effective coupling constant at the scale of the proton, and for the other particles it's the same. So you have to do it rigorously, and then you can get really good particle predictions, particle mass predictions, and that's what I accomplished in 2023. And in the same year, I used space particle dualism to also predict the mass of the muon and the tauon, which the second and third generation particles. And the only other theory, it's actually just a formula. Other theory is the Koide formula by a Japanese person, and but that only allows you to calculate a third particle mass by using two. Like you have three generations. For example, you take the electron and the tau, then you can predict the muon mass. But there's no theory behind it. There's no explanation behind it. It's just a formula, and he found it just by pure luck. And I derived that formula from my theory, but it's actually derived completely from the mechanics of my theory. This part of the theory is the core space particle dualism, and so basically I'm saying that you can treat muons as merged space quanta. Like it's like you have merging black holes, then
Yeah.
you have merging particles,
Mhm.
and that's quite funny because the whole theory started off as a analogy between black holes and particles,
Mhm.
because the size of these space quanta is basically proportional to the inertial mass or the energy of the particle. And so it's very much like a black hole, but with a different scale factor, with a different proportionality constant. It's basically like a black hole, but scaled up to the strength of electromagnetism, or the basically the quantum forces,
Mhm. Mhm.
and that's why it's quite big. So the elementary space of a resting electron would be 10 to the power of minus 21 um, meters.
Mhm.
And at 10 to the power of minus 17 meter, 9 times 10 to the power of minus 17 meters, I think it is, um, the wavelength becomes smaller than the size of the particle itself. And that's why CERN is not finding any new particles, because at the energies they are probing, they're, it's like you're trying to find something or research something smaller than your fingers by
Yeah.
using your fingers. You cannot do that.
Right.
So that's how I explain it. There are only three generations of particles and no only three generations of particles and no new particles whatsoever now at CERN.
So what about the, just out of curiosity, in this picture, where does the Higgs particle comes into play, or does it, or it's irrelevant?
Actually, I actually predict the mass of the Higgs, but I think if I remember correctly, it's the mass or the energy where the space quanta becomes bigger than the wavelength. Um, well, at least it fits the Higgs mass pretty well. Um, but I don't have a specific role for the Higgs. It's simply a spin zero particle, and I don't think that the standard model really predicted its mass. The standard model doesn't predict any particle mass. Okay, not any, but very few. It might predict the mass of the Z boson. Yeah, but that's about it. Um,
But you do
yeah, and I don't know for a role of it. I just know it's there for symmetry reasons. I mean, it was predicted in 1969 already by Peter Higgs, and nobody really predicted its mass before it. I heard that somebody predicted its mass shortly before it was discovered, but I don't know much about that.
yeah.
The Standard Model certainly did not predict the mass.
Yeah, that's true. That's correct. But someone did. That's correct. And so the question
Mm.
is, does your theory also predict its mass, or it's completely irrelevant, the Higgs,
Yeah,
whatever?
it seems so. It
Okay.
seems so.
Uh-huh.
But it's not relevant in I don't believe in the Higgs mechanism. I mean, it doesn't predict any mass. If the Higgs mechanism was useful, it would predict masses, but it doesn't. The electromagnetic mass theory predicts masses. Well, the electromagnetic mass theory doesn't predict masses either at first sight. I was looking at it for many years and I couldn't see how to predict mass with it because it's kind of circular. You're saying that
Yeah.
it's the energy and the force field of the electron, but if you calculate that energy, you're already using some measured value. So, but then if you use the coupling constants, then you truly can predict masses.
Mm-hmm. 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 Mm-hmm.
I actually published a paper about predicting the mass of particles, and that, but that was at the stage where I was still stuck at that circular argument where you have to use the known properties of the electron, predict the mass of the electron. It's circular. So the breakthrough in that came in 2023, and but that paper was published in 2018, and that's why I find publishing papers so um, like in journals so unproductive because then you have to change your paper and if it's a big change you have to republish it, and that's why people, all professors, they have like 500 papers,
Correct. Yeah.
but they
Yeah.
haven't really not necessarily done more research than some other researcher that has, let's say, in my example, 70 papers. It's just the difference is that you have to republish every time you make a small
But you,
change.
but in
And
your,
I don't do that. I just update my papers.
but your book reflects that, or you have to change your book.
Yeah, you can update. It's much easier to update a book than a paper. And every update you can see it in the beginning of every chapter you have a list of breakthroughs. So every chapter here there's a timeline and there are dates.
Yeah. Right.
So I basically have a date for everything I've ever done.
Okay.
And so I can just search in my book, what did I do on this day some years ago? And then I sometimes post it on Facebook when I don't, and when I'm not very busy.
Yeah. So, but this latest version that is in Amazon, it has the correct framework, correct? If I understand what you're
Yeah,
saying,
it's always the most correct.
most correct
The
one.
latest version is always the most correct version, but it's very important to get the name right because it's the complete guide to quantum gravity and not some other titles that are on Amazon.
Oh, okay.
Because I lost my mobile phone, the card. Like when you travel a lot and you leave the country, then the card is not valid anymore, or you lose it easily because it's so tiny.
Yeah.
This time that I returned to Germany is actually the first time that I kept my old number.
Okay.
So that's good. Otherwise, I would might have to have published my book again. Like it was republished two times. The original title was Quantum Gravity and the Role of Consciousness in Physics. And that's actually the version that my current sponsor read and sponsored me on the basis of. But I was surprised by that because it's a very old version from 2020, and it has
So
in that
what?
version only the cosmology part was really successful.
So what is the name of this one in particular again? Can you remind me?
Yeah, the complete guide to quantum gravity
The
because
complete.
it's really thick, so I thought it should be called the complete guide. The original version was talking much more about consciousness and
Okay. I will. I will bet.
it had like the philosophical outline and everything, but
Okay.
less math.
Okay. I see. And who's your sponsor? Who's sponsoring you on this? All this? Just out of curiosity.
OSS Capital, some
Okay.
yeah, some US company. Yeah.
Okay. Um, okay, so then,
I have two sponsors, not one. Yeah, one
mm,
in Swiss and one in the US. Hmm.
okay, okay. Um, um, yeah, because I was wondering, how do you take time to do all this research, and how do you get paid to do this research? How do you engage yourself with this kind of research commitment? How do you manage this? It's quite incredible.
Yeah, thanks. Well, since I've done this for a long time, but since 2019, my research is really successful, and since 2020, I get sponsored. My first sponsor was from China, from 2020 till 2022. That was, but that was both for physics, but also more for my etymology research. Yeah. Um, and then I got the sponsor from Swiss, and since last year, November last year, I have this US sponsor.
Okay, cool.
And without those sponsors, yeah, I don't think uh, I couldn't do. I would have to do some other work
Yeah.
as well.
So, but these are private companies, right? Not academia. It's
Yeah.
outside. And so, what is their interest in this direction? Because normally companies are dedicated to profit. They're profit based, and in your
Yeah,
case,
it can be very profitable once you. Well, I don't think all companies are behind profit, but it's certainly profitable if you have the theory that basically leads to new technology, because all the technology that people can make now is based on old physics. So if you have new physics, you can have new technology. You can build material analyzers.
yeah,
So for that, you have to measure force very accurately. And if you buy a regular force sensor and they want to be very accurate, they build a force restoration mechanism and that actually screws it all up, because then you're not measuring really force but mass. But they don't care about it. They don't care that a robot can feel something different when it's at the 10th floor versus being in the first floor.
yeah,
They are interested in force outside of gravitational force.
yeah.
And I could use a gravimeter, but you cannot swap out the test mass in a gravimeter, because the extreme accuracy of a gravimeter depends on it being very rigid installed there, and nobody can take it out. If you take it out, you lose some of the accuracy. But
Mhm,
I think you wouldn't really lose the relative accuracy. I guess you would lose the absolute accuracy.
mhm,
But I'm not interested in absolute gravitational force, because I'm only looking at differences between elements. So I wouldn't be bothered by that. But a regular gravimeter is already the display is already displaying free fall acceleration instead of force. So already using the mass of the test mass to get the actual free fall acceleration. And that's not what I'm interested in. I'm interested in swapping out different test masses. So if you use the regular gravimeter and you were able to somehow open it and swap the test mass, then you would just get some nonsense result on the screen, because it's still assuming the original test masses inside.
So, in fact, I was going to ask you about this question regarding this the free fall experiment, and so this is the thought
Mm.
experiment by Galileo, but then in vacuum, when you do actually experiments like recent experiments, when you leave objects of different material and different sizes, they fall exactly at the same rate, and so
No, they don't fall exactly at the same rate. It's just that nobody's first of all, you have to have different compositions. And the most famous video that convinces most of the lay people that the equivalence principle is right is a video by Brian Cox from England, where he's in some NASA laboratory, and they pump out all the air from some big room,
yeah,
and they let a feather and a bowling ball fall.
yeah,
I mean, I've done free fall experiments myself. If you want to observe the difference between elements with your own eyes, you need at least like 40, 50 meters. 100-meter should be, if you want to observe differences of like this much, you need like 100 meters already. So it's laughable to just let a bowling ball drop and a feather drop and say, oh, they're the same. Well, this is actually just showing the layman that mass doesn't matter. And I agree with that. Of course, mass doesn't matter. Can have an elephant falling and a mouse falling, and they will fall at the same rate because it doesn't depend on mass, but it does depend on chemical composition. And a mouse and an elephant, they have basically the same chemical composition. And a feather and a bowling ball actually don't necessarily have a very different composition because the feather is made of carbon, is carbon based, and bowling ball is made of rubber, and there's a lot of carbon in there too. So it's totally not an experiment that is not targeting chemical composition. And people who do that kind of experiment to show the layman that they don't even know what a theory that is composition dependent would actually predict how big the effect would be.
Okay, you're going too fast. This is an important aspect, which is really what I wanted to get at, because indeed I was convinced, and in fact the whole academia is convinced that things fall at the same rate, and particularly because of this kind of experiments that Brian Cox did.
I don't think that people in academia are using this experiment as evidence. They're using experiment as evidence, which are totally misguided. Like they don't. I mean, every measurement of big G ever conducted violates the equivalence principle because if you take them all and you look at the chemical composition, every one of those elements falls in line. I have a graph for that, and I'm sure you have seen it, the big G graph.
Uh,
Let me
I
see
don't
if I
know
can
yet.
find it in the
Yeah,
book.
yeah, maybe you can show me.
1 second. I also have it in a folder, but yeah, let me take it from some folder here. Where is it? Okay, here.
So let's see. So what is in the x-axis and what is in the y-axis?
So you can see the chemical compositions here, and they seem to be like in some random order, but it's not random. It's in the order of increasing binding energy per mass. So that's why iron is on the top. If you made this diagram to be in the order of atomic number, then you would see it peak in iron. Iron would be in the middle, not in the end. And sometimes I use that kind of diagram, but yeah, it's just nicer and easier to calculate the hierarchical order when you calculate the p-value of the hierarchical order when
Sorry.
it's arranged neatly with the increasing predicted values. So the prediction line is the blue line is the prediction line, and those are the measurements. And accurate measurements are possible since 1969, I would say, since the 70s basically, but yeah.
Sorry, can
And
you?
the only one that is before the 70s is Hale. He did some very good work. Can see several of his values there. And he found different gravitational constants for different materials. And he was confused by that. And what he did is he repeated the Atwood experiment, which Einstein cited for his theory as evidence. But that's so extremely misguided because, first of all, in that experiment, different elements actually do not overlap. They do not at all overlap. And that actually disproves the equivalence principle. But in that experiment, it's constructed in a way that makes the differences between different elements very tiny. So here you can see the different elements. And the experiment was done very long time ago and with very strange materials like tallow. And yeah, a bit complicated to calculate, but
Yeah.
I
So
did
what
calculate
is
them.
again? What is in the x-axis here? Is it the binding energy?
In both cases, the y-axis has the gravitational constants here.
Yeah, and the x-axis again is the binding energy over what?
The x-axis is nothing. It's just listing the different elements here,
Yeah,
but
but
it goes into the direction of increasing binding energy. But the binding energy is not written down in any axis. I only have two axes, so I'm using most diagrams are not dealing with infinite numbers of chemical elements. So my x-axis is just the chemical compositions. So for example, Hubler, 1995.
Yeah.
That's water and iron. So the source mass was water and the test mass was iron. If both of them were water, it would be down here. It would be very low,
Mhm.
somewhere 6.6660 or so. I don't quite remember, something like that.
Right. Right.
Yeah, and here you have pairs of materials and you look at the ratio between the pairs, the difference. And now here the difference is extremely small. They're like 1 millionth
Right. That's highly, yeah.
or smaller. And so the reason they're so small and why Einstein, or why the one who measured this, Edwish, why he still believed that it confirms the equivalence principle, although the error bars were not overlapping. The reason for that is, well, because it's so tiny. The differences are so tiny. And the reason they're so tiny is actually quite simple. The different materials are part of one beam, different sides of one beam, and the experiments are comparing the the gravitational force versus the centrifugal force that is induced by the rotation of Earth.
Mhm. Mhm.
So those are very small effects, and actually you have to calculate out the rotation that's already induced by the rotation of the Earth, and and you have to measure tiny rotations induced by difference in material. And
Mhm.
some of them overlap with the null hypothesis, which is here at 0,
Right.
but not all of them, just a few of them, and they don't overlap with each other much. And okay, they're a little bit, but not all of them. And and basically the only reason, because since they are part of the same beam, that in my mind there shouldn't be even any effect, composition dependent effect. But because one of the masses on the one side is suspended and hanging in a lower gravitational potential, that's why there's a kind of difference in the how the gravity is evaluated on those two different points, and that creates a tiny effect. And that's the one part of my book where actually rounding up would be totally wrong, because here you have to look at all the decimal places and calculate those tiny effects.
Right. 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 I see. Mhm. Okay. Okay. So I see. So this is, so what you're saying is that it doesn't, so the acceleration is not the same. It's really material
They're,
dependent.
they're always looking at experiments which are likely to confirm their belief. So the Atwish experiment is constructed in a way that's it's very non-intuitive, and actually, I don't blame you if you can't fully understand how it works. It's a bit challenging, and and it's very indirect. It's not. People imagine, oh, people just drop things and measure the free fall acceleration. No, they never do that. Like if you look at on Wikipedia tests of the equivalence principle, they list one ancient Greek test free
No, right.
fall experiment. Like what ancient like it's not a real experiment. And then Galileo, who never even did this
Yeah.
experiment, it's just a thought experiment. And then they have only one modern experiment, Neil Bauer, and he did a laughable job. I mean, he was 60 centimeters height. Like here I have 2 meters, and it's already the minimum. You can't go below 2 meters. It's too tiny. Like and you need very different materials if you want to still be able to measure it. And he took 60 centimeters, and that's not even the worst part. The worst part is he only measured the terminal velocity. So from my two photo gates, the one on top and the one at the bottom, I don't know if
Yeah.
you can
Yeah.
see it there. He only took the bottom one, and if you just take sorry, is my camera still working? Can you hear me?
Yeah. I can hear, but I don't see you, but it's okay.
Um, wait a second. Mm. Yeah, I shouldn't have lifted up the computer. Okay, now I switch it on again.
But what if you would
Yeah.
do your experiments in vacuum? like copying what uh, this experiment comparing the weather, the feather and the ball. What if you would do your experiments there? What would you expect?
Well, I would have to calculate the gravitational constant of a feather, which is a bit complicated, but I guess you can have some small chemical formula for the like average composition. Yeah, and the bowling ball, I'm not sure what it exactly is the composition. But if you're doing an experiment with what was the height there, like
I think it
4 meters to 5 meters? I don't know. In that
I,
video of Cox,
yeah, I can't
I
remember,
mean,
but it was high, in fact, because it was a chamber that you use for I can't remember exactly, but I think it was quite high, even maybe.
okay, let's take an example. The most extreme example that you can have is rubber and zinc or rubber and steel. That would be at this height of 2 meters. It's 0.0007 seconds, and the human mind cannot even see that fast. And of course, if you calculate the height difference, it would be, I would say, it would be like a millimeter or so,
Yeah,
like
right.
millimeter or two. Yeah, I think only 1 millimeter. I mean, for 100 meters, you get like for lead and steel, you get a difference of like 5 centimeters or so. Like those are tiny differences. You need 100 meters. You can see nothing at the height of 5 meters.
Okay, so but then basically your underlying point is that there is no universal um, constant, so to say, somehow. It's material dependent, and
Yeah,
the
but there's still the chromogravity constant, which is the gravity per quark, and you could also write down the gravity per baryon, and those are all perfectly constant.
yeah, yeah, exactly. So yeah, exactly. When you move to mass, then it's not constant. Yeah, right,
Yeah,
right.
because it has nothing to do with mass. That's why.
Yeah,
And then you may ask, why do we need to even care about it or write it down if gravity has nothing to do with mass? Why do we have to write down the gravity per mass unit? Well, that's because when you do calculations in gravity, you always have, like when you have escape velocity or free fall acceleration, you always have kinetic energy or force or something including mass on the left side, and on the right side you have gravitational force, or you have gravitational potential energy, something like that, and that
yeah,
does not include mass, but you have mass involved. That's why you should use gravitation constant in the mass formalism. Then there's also the quark formalism where you just write down the gravitational constant of quarks, the chromogravity constant. You multiply that only with the mass of quarks inside the first mass and the mass of quarks inside the second mass. Divide by the square of the distance. And when you do calculations like that, then the small m, the mass doesn't cancel out, does not have nothing to cancel out with, but you get a fixed ratio. You have a fixed number of quarks and a fixed number of fixed mass for every chemical composition.
right, right.
But if you increase the mass using mass inflation, like using particle accelerators, then you can increase the mass, then you can change gravity. But nobody has ever done that. Nobody has ever heated up something so much that its mass increases.
Mhm, mhm,
Nobody has ever done that,
right.
and
Good.
and that's something I want to do in the far future. But
Okay, we
yeah,
have
it
less
would
than a
need
minute.
Elon Musk level funding.
We have less than a minute. I think it's going to
Okay.
close. Maybe we could catch up in a different. I mean, if you want to continue, we can continue. Or so we'll have to wait maybe 10 minutes, and then we come back again. Then we'll finish. That's the
Yeah,
last.
if you like.
Yeah. Okay. So
Yeah, sure.
yeah, I will. So I'll stop now, and then we'll continue.
Maybe it's best to just let it run out on its own.
Yeah.